So moving on to finish up chapter 36 in special relativity. So here again are the postulates of special relativity. All the laws of physics are the same in all inertial reference frames, and what this implies is that the speed of light in a vacuum is always c, independent of the observer. So we were left off the last of the pre-class because we ended up with this idea of time dilation. Here's the funky looking equation. This is the proper time. This is the dilated time interval. So this is the proper time is a time measured in the frame where the events happen at the same place. And the dilated time interval is the time measured in the frame that's moving with respect to the events. And so you got to be real careful about which time is which. So proper time again is the time measured in the frame where the events happen at the same place. It is not the real time. There is no real time. All observers measure a correct time, but just we want to be able to keep them straight so we can figure out which one is which in our equations and what we're talking about. So here's an example to give it a try. So Alan and Beth operate clocks at 2 points on the Earth's surface, A and B. Clarissa rides a train at a constant speed between the 2 points. Which registers the greatest time interval between the events, Clarissa's watch or the difference between Alan and Beth's clocks? And let's just assume these people have super accurate clocks. So give us a try and let me know what you think. Okay, so first of all, in our equation, if we look at our equation, it looks like this here. So it's delta t equals delta tau, and then it's divided by this little guy here. So v squared over c squared. So first of all, on the bottom side, if there's any relative velocity, this is always less than 1. Okay, and so you divide less than 1, that means delta t. So in this equation, as long as the velocity is not 0, delta t is always going to be bigger than delta tau. And if you include the case where the velocity is 0, they're just equal. Okay, so in general, if there is some velocity, the proper time is always less than the dilated time. That's the whole idea about this. And so if we look here, the proper time is going to be the smaller time. And so the proper time is where events happen at the same position, or another way to think about it is the same person can measure the events. And so if you think about Clarissa's watch, okay, it's with her, so she goes from point A to point B. So Clarissa travels from here to here, so she takes the time measurement at A and then a time measurement at B. Okay, so according to her, the events happen at the same place. They're right where she's sitting because she's moving along from event to event. Alan and Beth have to measure it on separate clocks, okay, and it's not at the same place. The beginning is at Alan and the ending is at Beth. So Clarissa is going to measure the proper time, which is the delta tau, which means Alan and Beth will measure the longest time, which is what we're asking here. What's the greatest time interval? Okay, so now once we have time dilation, there's this other effect that kind of comes along with it that's called length contraction. And so we're following along here with night. And so consider a rocket which travels from the sun to Saturn at speed v. And so here's the picture. It starts at the sun and goes to Saturn. It covers some length L. And so this is in the reference frame here of the solar system. Okay, it's watching the rocket go from the sun to Saturn. So in the reference frame, you're watching it go from here to here. And basically they say, okay, so the distance traveled is L, the velocity is V, and so you can make this little equation that says velocity equals L divided by delta t, the time it takes for the trip to happen. And that's, again, from observers who are standing still relative to the solar system, are watching the rocket do this. Now, if we switch to the frame of the rocket, what happens is now the rocket, so kind of like we were doing in class, so now the sun is heading backwards with some velocity, and Saturn's moving towards the rocket with some velocity, and there's some new distance that we'll call L prime. All right, so Saturn moves the distance L prime in the time delta t, which is the proper time, because now it's the time measured by the rocket. And we know that the proper time, if there is a velocity, is less than the delta t, the dilated time. And so what happens is, since the Saturn and the sun are moving with the same velocity the rocket was, okay, then the length in this case has to be a smaller length. And the way Knight goes about thinking about that is he draws this equation here like this. So in the first case, it's L divided by delta t. In the second case, it's L prime, and we'll just call this the proper time on the bottom. Okay, so since the proper time is smaller, so it's smaller, L prime has to be smaller in order for the ratio of them to be the velocity. Okay, in either frame, in the solar system frame, the rocket ship goes with V. In the frame of the rocket ship, the planets are going with V. So the velocity in both frames is the same, just for different objects. Then what Knight does is, okay, so he takes our new equation, delta t is equal to tau over the 1 minus beta. And of course, again, I'm not sure if I mentioned this before, but beta is just what they call v divided by c. It's just a little convenient way of writing. So this is a nice way of writing that, just to save some time. And so if you plug that in for the delta tau, okay, you get what we have here, and you get what's called length contraction. And it's this equation right here. All right, and basically L prime is the length measured by something that's moving past an object. All right, and L is what we call the proper length. And so the proper length is the length measured in the frame where the objects are at rest. And so L prime is what the length of the object when it's at rest. Or I'm sorry, lowercase l is length of the object when it's at rest. L prime is a length that's measured by something that's moving past this object. All right, so the length of any object is less when it's measured in a reference frame in which the object is moving. So let's look here, thinking about this idea of proper length. So the same example, Alan and Beth are looking at synchronized clocks at 2 points, A and B, A for Alan, B for Beth. Clarissa rides a train at a constant speed between the 2 points. Who measures the proper length of the train? So think this one over and let me know what you think. So the proper length of the train is going to be measured by the person who's at rest relative to the train, and that's going to be Clarissa. Okay, so Clarissa would be answer B in this case here. And here's an example using length contraction. So in my spaceship of proper length 5 meters, I fly past you at a speed of 0.8 the speed of light. What do you measure the length of my ship to be? So give this one a try and see what you think. Right, hopefully you got that it was 3 meters. So I take my new fancy equation. L0 is the proper length. Okay, and the proper length is when I'm at rest. So I'm at rest with my spaceship because in my frame, me and the spaceship are not moving. Okay, it's the same thing with Clarissa's example a couple slides ago. And so that would be the proper length would be the 5 meters. So here's my 5 meters, and I put in my 0.8 c into here. Okay, remember that basically the c and the c here will cancel, which makes your life really nice. And you do this, you get a length of 3 meters. Now, moving on, we're going to talk a little bit here about space-time coordinates. And so in every frame, so here's the S frame and the S prime frame. Remember, the S prime is the one that's generally moving. You have 4 coordinates. And so we call them x, y, z, the usual coordinates, and then time is now considered to be on equal footing with x, y, and z. And in the moving frame, you have x prime, y prime, z prime, and t prime. And so sometimes we talk about these as space-time coordinates. And so it's basically all the 4 coordinates of an event. Okay, an event has 4 things that represent it. Its position, x, y, and z, and then its time. And here is the Lorentz transformations. We're not going to use these too much, but they can be handy sometimes. So I wanted to point them out to you. And this is basically how you can transform between the x prime frame and the x in the unprimed frame. All right, and it's basically, if you remember, we did this in class dealing with the Galileo version. So here's the Galileo version. It's a lot easier, simpler than the Einstein version, the Lorentz transformations, but it's the same idea. You're transferring from one to the other. And the one thing is that they make another little calculation or little simplified thing is that they call this factor 1 over radical 1 minus beta squared. They call that gamma. So here there's a gamma, and here there's a gamma over here. Okay, and so what happens now is that basically the distances x are different and the time is different. Okay, over here they even write it, but over here in Galileo's version, the times are just always the same. Moving on, we find that many things are impacted by relativity. And so here is relativistic momentum. So it looks like our regular momentum, all right, but it's got that factor. And so sometimes you'll see it written like this here with that gamma factor like we were talking about. just a slide before. And so P is the relativistic momentum. M0 is something we're going to call the rest mass. Okay, we're going to talk about that. And V again is the velocity relative to the objects that you're talking about. And here's an equation, or a graph rather, showing you how relativistic momentum goes with non-relativistic momentum. Okay, and so basically as the speed of the relative frames increase. Okay, and so we're saying that there's some object that's going m0 times v, all right, and now if its velocity was to increase, all right, what happens? You get this curve here that gets steeper and steeper as you go along. And so what this curve turns out to be is essentially just a graph of that gamma that we were talking about. Okay, so this guy over here, this sort of graph of this gamma here. But you see that basically as the speed gets closer to c, it gets very, very steep. And we finally here get to what's one of the most probably famous equations. It's second, maybe even first, over F equals ma, is another thing that, so basically this idea that speed of light is always constant leads us to this idea that the energy for something equals this equation here. And this is oftentimes written is this way over here with the gamma, so it'll be a gamma m0 c squared. And what happens is when the velocity of the object is 0, all right, this guy just goes to 0, and you get E equals mc squared. And so E equals mc squared is the energy when something is at rest. And we call that the rest energy. So this right here would be the rest energy. Then there's this gamma factor that basically gets larger or smaller and smaller with higher velocities and makes your energy more and more with higher velocities. And so this is really important. So what Einstein got out of the relativity, so basically he started all of this by saying that the speed of light must be constant to all observers. And here he gets that energy and mass are the same thing. So up to this point, there was conservation of energy, conservation of mass. They were two separate things, but now they're part of the same thing. Okay, you can think about mass as in some way being kind of like frozen energy in a sense. What they like to do in the book is to express the kinetic energy, and the way you do that is you think the total energy is just this rest energy plus the kinetic energy. And so we know that our rest energy is the m0 c squared, and we know the equation from that from the last slide. You can write the kinetic energy here. It's basically this term, which is the total energy minus the rest energy. And so this is a really important idea, okay, and so one of the places where this really comes into play is nuclear reactions. All right, so for instance, in the sun, up to this point, nobody really knew how the sun worked, okay? If the sun worked like, say, some sort of a steam engine or something, okay, just from the chemical energy of the elements, it would have died a long time ago. But what happens is in the sun you have fusion, where two atoms combine to make a third. So initially two hydrogens combine to make a helium. If you were to get the mass of the helium, it's a little bit less than the two hydrogens, and this little bit less of energy is converted into energy. So this little tiny difference in mass is converted into energy. And of course, from this equation, it's a mass and it's times c squared, which is a huge number. So a tiny bit of mass equals an awful lot of energy. And then in atomic bombs, we use the same idea, but kind of the opposite idea. You do what's called fission, where one atom splits to make two atoms. And again, it's the same idea. The mass of the two resultants is less than that of the original atom. And here is a picture from the book actually showing the process of how this works. All right, and so you can use a uranium-235 nucleus, and so this is what we actually do inside nuclear reactors. And so you take this, and what you do is you shoot a neutron at it. So here's a neutron that's hitting it, and what it basically does is it kind of makes it unstable. So uranium-236 is unstable, and it breaks off. It breaks off into two smaller pieces, and then three neutrons here, here, and here. And if you again were to find the mass of the resultants, it's a little bit less. Okay, it's a really tiny amount. It's like 1.85 U of mass. So it's a really tiny amount. But again, because E equals mc squared, all right, that turns into quite a bit of energy. And then to get a chain reaction, you set this up so that these three neutrons go and hit another uranium, making it unstable, and the whole process can be self-sustaining. And so this generates heat and energy, and this is how you can do these processes. All right, one last thing. We've been kind of hinting at this a few times, but another consequence of what Einstein said is that there's a cosmic speed limit, okay? And then what that means is that nothing can travel faster than the speed of light. If you look at this equation here, okay, from our time dilation, okay, as this approaches c, you end up dividing this by 0. Well, we know dividing by 0 is bad, and what that means is the time becomes infinite. Okay, if you look at your equation for momentum, that means the momentum is infinite. All right, and so there's according to what we believe, there's a cosmic speed limit. And one way you can think about that is if something could go faster than the speed of light, it would violate what they call causality. And I think the example I like to use with that is if I have a remote control, all right, and so I push the remote control, then my TV changes channels. If you could go faster than the speed of light, all right, you would be able there would be a frame that would be possible for you to see my television channel change, and then I would hit the button on my remote control. And so cause and effect would be messed up, and that's something that's we don't like when that's messed up. And so that's one thing that would be really bad if that was messed up. And so finally, special relativity has been tested many times. Never has it been violated. In fact, some numbers that come as a consequence of special relativity have been tested basically as accurate as just about any number in science. And so now these are just basically a more general form of Newton's and others' equations. Okay, so for instance, with the momentum, it's this big ugly thing here, but for everyday speeds like we deal with, this bottom part is basically 1, and the momentum is just m times v like we like. Okay, all right.